Today, our mission is to really dig into the fundamentals of linear regression. Not just building the model, but, well, making sure it actually works. We're focusing specifically on the theory, the concepts, and those diagnostic tools we use to check assumptions, especially when our data points are collected over time.
That's absolutely the core issue. If you've ever needed to present results from a regression, predicting sales maybe, or environmental trends, those coefficients, those betas, they're only as good as the foundation they sit on. So our goal today is to help you get competent quickly at spotting and understanding when those standard assumptions are violated. Because ultimately, the validity of everything you claim statistically, it all hinges on how those error terms behave.
Right. And when we write out that simple linear regression model, the SLR, or what we estimate later as the residual, epsilon t, it's everything, isn't it? It's all the stuff the simple line didn't capture. And if there's some pattern left in that leftover stuff, well, we've got a problem.
Exactly. To do proper statistical inference, to actually trust your confidence intervals, your prediction bands, your p-values, the residuals need to meet three standard ordinary least squares, or OLS, assumptions.
Okay, let's lay them out. First up, homoscedasticity. Sounds complicated, but it just means the residuals have a common variance. The spread, the variability of the errors shouldn't really widen or narrow depending on where you look in your data.
Correct. Second, uncorrelatedness. The errors can't be related to each other. An error at one point in time shouldn't give you any clue about the error at the next point in time.
Makes sense. And the third one is normality. Basically that the residuals follow a normal distribution, that classic bell curve.
Now, we tend to focus heavily on those first two, uncorrelatedness and constant variance, for a very practical reason. It comes down to the Gauss-Markov theorem. This theorem is fundamental in linear modeling.
And that theorem gives us something pretty powerful, right?
It gives us efficiency.
Yeah.
What it states is, if your residuals are uncorrelated and they have that common variance, the homoscedasticity we mentioned, then the estimators you get for your coefficients, your betas, they are the best linear unbiased estimators. BLOE for short.
Okay, BLOE. But why should you, listening, care that they're BLOE? What does best actually mean here?
Best means minimum variance. And that's huge. Minimum variance means your estimates for those beta coefficients are as precise, as sharp as they can possibly be among a certain class of estimators. It translates directly to narrower confidence intervals around those estimates. You essentially need less data to be confident about your findings. It makes your model more powerful, more reliable.
Maximum precision, that's the goal. Now, you mentioned uncorrelatedness. There's a related idea, independence, that sometimes tricks people up.
Yes, independence is actually a stronger condition. If your residuals are truly independent and identically distributed and they're normal, then all three of those OLS properties we listed, they're automatically satisfied. Independence implies uncorrelatedness, but the reverse isn't necessarily true. Being independent is a much higher bar.
So IID normal residuals are the ideal scenario. We've basically neutralized the error term, but let's be honest, real data is messy. What's the real danger if we miss these assumptions, even if the model, say, looks okay on a basic scatter plot?
The danger is statistical illusion, really, overconfidence. Even if your model seems to predict, okay, if those OLS assumptions fail, then all your formal inference, your t-tests, your p-values, how wide your confidence intervals should be, all of that becomes incorrect, potentially very misleading. You might claim a predictor is significant when it isn't, or you might think your prediction interval is tight when it should actually be much wider. That's why residual analysis isn't optional. It's like the forensic audit of your model.
Okay, let's start that audit. First tech, homoscedasticity, constant variance. Visually, when I'm looking at my residuals, what's the first sign that variance isn't constant?
Well, the standard approach is visual diagnostics. You plot your estimated residuals against a few different things, usually against time, against the fitted values from your model, and sometimes against the predictor variable itself. What you want to see is just randomness, a scatter of points fluctuating around that zero line, forming a sort of constant band or cloud. The height, the amplitude of that cloud shouldn't systematically increase or decrease as you move along the x-axis.
And what if I see that classic funnel or cone shape, where the points start tightly packed and then spread out dramatically? Is the first reaction just to scrap the model?
Rarely the very first step, unless the model is just fundamentally wrong for the data. That widening cone is a clear sign of heteroscedasticity, or non-constant variance. Before throwing the model out, you typically look for remedies. Often, transforming one of your variables can help. For example, taking the logarithm of the dependent variable y can sometimes compress those larger values and stabilize the variance. It's about respecifying the relationship slightly.
Okay, stabilizing variance is key. But what if the issue isn't the size of the error, but its timing? Let's talk about uncorrelatedness. This is super relevant for time series data, right?
Oh, absolutely. This is where time series analysis often really diverges from simple cross-sectional stuff. When you collect data sequentially over time, daily stock prices, monthly rainfall, whatever, there's a very high chance that the error from one period might influence the error in the next period. This kind of memory or persistence in the errors is called autocorrelation, or sometimes serial correlation.
Right, like in economics. If there's an unexpectedly high inflation figure this month, it's probably more likely to be higher than average next month, too. The error seems to have some momentum.
Exactly that kind of inertia. A common way to model this, theoretically, is using what's called a first-order autoregressive model for the residuals, an AR1 model. The idea is simple. Today's residual is partly determined by yesterday's residual, scaled by some coefficient plus a new random shock term, the autoregression coefficient. It measures the strength of that persistence.
But so if roll's are large and positive, the error is sticky, it hangs around, what happens if we just ignore that and use standard OLS anyway?
Well, interestingly, your coefficient estimates, they actually remain unbiased. On average, they still point to the right true value.
Right.
But you lose that crucial BLUE property. They are no longer the best estimators, they become inefficient. And perhaps more critically, the way we usually estimate the error variance, the mean squared error, or MSE. It can seriously underestimate the true variance when positive autocorrelation is present.
So the danger is our calculations are telling us the error is smaller than it really is.
Precisely. If your estimate of the variance is too low, your standard errors will be too small. That makes your t-statistics look bigger than they should be, and your confidence intervals seem deceptively narrow. You might conclude a predictor is statistically significant when, in reality, the relationship is much fuzzier because of that correlated error structure. It basically invalidates the standard F&T tests you rely on.
Okay, so how do we detect this autocorrelation? The Durbin-Watson test is the classic tool here. What's the basic idea behind that DW statistic?
The DW statistic is clever. It essentially compares the squared differences between adjacent residuals to the overall sum of squared residuals. It produces a value between 0 and 4. Now think about positive autocorrelation. If a positive residual tends to be followed by another positive one and negative by negative, the differences between adjacent residuals will be small. So a DW statistic close to 0 indicates strong positive autocorrelation.
Got it. Low DW means positive correlation.
Yes. And conversely, if the residuals frequently flip signs positive then positive, that's negative autocorrelation. The differences between adjacent terms will be large, pushing the DW statistic up towards 4. A value near 2 generally suggests no significant autocorrelation. So the test usually checks the null hypothesis against an alternative, positive, negative, or just non-zero. Positive is the most common issue in practice.
And there's another check too, the runs test, a non-parametric one.
Right. The runs test offers a different angle. It's quite intuitive. It looks directly at the sequence of signs of the residuals positive or negative. A run is just a sequence of identical signs. If the residuals are truly random, you'd expect a certain number of runs. Too few runs suggest persistence, like long stretches of positives followed by long stretches of negatives. That points to positive autocorrelation. Too many runs suggests the signs are flipping back and forth too often, indicating negative autocorrelation. It's a neat way to check for non-randomness without assuming a specific error model like AR1.
Okay, let's move to the third diagnostic, normality. Checking if those residuals follow the bell curve. How do we tackle that?
We usually use a mix of visual checks and more formal numerical tests. The go-to visual tool is the quantile plot, or QQ plot. What you do is plot the ordered values of your actual residuals, the sample quantiles against the corresponding theoretical quantiles you'd expect from a perfect standard normal distribution.
So it compares what we have against the ideal benchmark.
Exactly. If your residuals are perfectly normally distributed, those points should fall right along a straight line on the QQ plot. The slope and intercept of that line relate to the standard deviation and mean of your residuals. Any systematic deviation from that straight line, like an S-curve, or points peeling away at the tails, is a visual clue suggesting non-normality. But, visual checks are subjective. How far off the line is too far? That's where numerical tests help.
Right, which leads us to something like the Shapiro-Wilk test.
The Shapiro-Wilk, or SW test, is a very common and quite powerful test for normality. It gives you that objective assessment. Its null hypothesis is that the data does come from a normally distributed population. The test calculates a statistic, W, which ranges between 0 and 1. Basically, it compares the best estimate of the variance based on the ordered data to the usual sample variance. Values of W close to 1 provide strong evidence in favor of normality. A small value, and a corresponding small p-value, would lead you to reject the null hypothesis of normality.
Okay, we've covered the main checks for simple linear regression. How does this scale up when we move to multiple linear regression, MLR, with several predictors, say p of them? The model just extends, right?
The underlying OLS assumptions about the error term epsilon remain exactly the same. We still need homoscedasticity, uncorrelatedness, and normality for valid inference. The main difference is computational. We usually express MLR using matrix algebra, bold symbol x plus bold symbol epsilon, and solving for the coefficient vector x symbol beta involves matrix operations, specifically inverting the bold symbol x matrix. We don't need the full math here, but it's important to remember this calculation requires that matrix to be invertible. If your predictors are too highly correlated with each other multi-collinearity, that inversion breaks down.
Ah, so adding more predictors introduces its own potential pitfalls, like multicollinearity. Assuming we can actually compute the coefficients, inference on individual parameters still uses the t-distribution.
Yes, but the degrees of freedom adjust. But before zooming in on individual coefficients with t-tests, we usually want a global check. Does the model as a whole have any explanatory power? That's the role of the overall f-test. It simultaneously tests whether all the slope coefficients are 0.
So the null hypothesis for the f-test, none of our predictors help explain why.
Exactly. If you can reject that null hypothesis based on the S statistic, it means at least one of your predictors is related to Y. It tells you the model is likely better than just using the mean of Y as your prediction. It suggests the model has some value, though it doesn't tell you how much value.
Right. And to gauge that how much value part, we look at the coefficient of determination. I sometimes feel this is a bit misleading, though. It always goes up when you add more variables.
That's a very fair point. Higher squared seems good, but its major weakness is exactly what you said. It never decreases when you add another predictor. Even if that predictor is completely useless garbage, it just keeps creeping up or stays the same.
Which is why we really should be looking at the adjusted chart.
Precisely. The adjust fixes that problem. It modifies the calculation by including a penalty for the number of predictors relative to the sample size. The formula essentially penalizes complexity. Adding a useless predictor that doesn't improve the fit enough to overcome the penalty will actually cause the adjustment to decrease. So it gives you a much more honest assessment of the model's explanatory power per predictor used. It rewards parsimony, getting a good fit with fewer variables.
This whole discussion really highlights that running the regression is often the easy part. The real skill, the real statistical craft, is in that careful, meticulous examination of the residuals.
It absolutely is. You could say the ultimate goal, especially in time series regression, is to build a model that successfully captures all the systematic information, the trends, the seasonality, the autocorrelation, such that what's left over, the residuals, behave like pure random noise. They should satisfy those OLS assumptions. That's when you earn the right to trust your p-values and confidence intervals.
And as you start doing this in practice, you inevitably run into tricky situations, conflicts between different diagnostic tests, for example. You might run, say, the Durbin-Watson test, and it screams autocorrelation, really strong positive serial correlation. But then you run the Shapiro-Wilk test on those same residuals, and it comes back saying, yep, looks perfectly normal.
That happens. It's more common than textbook examples suggest, and it leaves you with a puzzle. So here's something for you, the listener, to think about. If you know your inference is compromised by autocorrelation, but the normality assumption seems okay, which problem do you tackle first? And more subtly, could that strong autocorrelation itself be distorting the results of your normality test? Which violation is truly the root cause? That's the kind of challenge that bridges theory and real-world data analysis.